everybody, welcome back for activity 2. So in this lesson, 2-1, we're going to be talking about inductive reasoning. So this is going to be really important going forward when we start doing proofs, because we're going to have to be able to use reasoning to complete proofs. So in our targets today, what we're going to be doing is making conjectures by applying inductive reasoning, and then recognizing the limits that inductive reasoning can have, okay? So the materials you need today is your Springboard book, something to write with, and a highlighter, because we will have some new vocab coming in. So we should be on page 13 in your book. And we're going to talk about the ability to recognize patterns. Okay? So to recognize patterns is an important aspect of mathematics. Every math subject has patterns, okay? Whether it's an algebraic subject or if it's geometry, there's patterns everywhere in math, okay? So this inductive reasoning, what we're learning today, it's the process of observing data, recognizing patterns, and making a generalization. That generalization is called a conjecture, okay? So for example, if I go to a Mexican restaurant and I notice that lots of people are ordering tacos, I'm observing that, I might make a conjecture that say the tacos must taste good, okay? So that's kind of what that means. You're observing something and you form a generalization about that. So what I want you to do here is I want you to read through question 1, read this paragraph, and then you're going to use inductive reasoning to make a conjecture about which food probably caused the illness. This is like a food poisoning type situation. So go ahead and read through 1 and figure out what's your conjecture based on this observational data. Okay, so which food probably caused the illness? It's looking like the, what was it, the potato salad? Oh, pasta salad. It's looking like the pasta salad is what caused a lot of the issues with everybody. Okay, so again, this is just based on the information we knew and made everybody who had the pasta salad got sick. Okay. So now we're going to move into some more mathematical examples of inductive reasoning. So use reasoning to make a conjecture about the next 2 terms in the sequence and explain the pattern. So you can make a little note here what you think the pattern is and go ahead and find the next 2 terms. So I'm going to let you guys work through number 2 and I'll go over the answers in a minute here. So pause the video and we're going to go over those. Okay, so here are the solutions. So in A, it looks like they're using consecutive letters that are alternate, and the numbers are going up by multiples of 4. The one that's a little tricky is this bottom one, and this is using this little history lesson over here, where it's actually called the Fibonacci sequence. So what that means is they take these 2 numbers and they add them together. That gives you the next value. I would take these numbers here, add them together, and that's going to give me the next value. 2 plus 3 is 5. 3 plus 5 is 8. 8 plus 13 is 21. 21 plus 13 is 34. Okay, so there we go. All right, let's skip to the next page here. So we have 4 circles on the bottom of your book. So what we're going to do is use those 4 circles below. There's points on all of them, as you can see. So what we're going to do is draw all possible chords. So remember, a chord is just a line that goes from a point on the outer circle to any other point on the outside of a circle. Okay. These chords will form a number of non-overlapping regions in the interior of the circle. For each circle, count the number of regions. Okay, so let me go down to here. So in this first example, we have 2 points, right? So I only have 1 line to really connect here. So if I connect these points, the non-overlapping regions would be the 2 sections that it makes. Okay, so you can see here we have 1 section here and a second section there. Okay. If I do the same thing on the next circle using those 3 points, I can connect those 2. those two. But I can also connect these 2 points as well. Okay, so if I count the number of non-overlapping regions, I have 1, 2, 3, 4 regions, right? So I'm going to go back up and fill in this table. So when we had 2 points on the circle, we had 2 non-overlapping spots. When we had 3 points on the circle, we had 4 regions that were non-overlapping. Okay, let's do the next one. So this time we have, let's see, 1, 2, 3, 4 points on the circle. So I'm going to go ahead and start making connections. Making sure I don't overcount, and then this one can go here. Then the bottom one can connect here, and then all their points are already connected. So let's count the regions. I got 1, 2, 3, 4, 5, 6, 7, 8. 8 regions. So hopefully what you're starting to see a little bit here is a pattern starting to form. Okay. So you can go ahead and make a guess. Okay. If we have 5 points on the circle, okay, how many non-overlapping regions do you anticipate us having? Okay. So if we describe this pattern here, it kind of looks like it's going times 2 times 2. It's doubling every time, right? So hopefully if we have 5 sections, that means we should have 16 forms of non-overlapping regions, right? So let's just do this. I'm going to do it pretty quick here, but we have 1. Oopsies. And then this one here. So counting these up really fast. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So we did end up with 16 spots. Okay. All right, let's move on to the next page. So let's look at question 5. It says the diagram shows the first 3 figures in a pattern. Mario's conjecture that the 4th figure in the pattern will be the 3rd figure rotated 90 degrees clockwise. Is Marco's conjecture reasonable? So is his observation making sense, basically is what we're talking about. So what I did is I took a screenshot of the first figure. So he's saying the 4th figure would be the 3rd one, just rotated 90 degrees again. Okay, well, let's look at it like this. So I have this figure that I took a screenshot of. Now it doesn't want to move. Okay, and I'm going to actually rotate it. Okay, so if I rotate it 90 degrees, it does actually form that picture, right? If I rotate it 90 degrees again, well, there you go. There's that picture. So if I rotate it 90 degrees a 4th time, looks like Mario's conjecture is correct. Okay, it's reasonable. It's just rotating the picture 90 degrees for every pattern. Okay, so I want you guys to try 6 then. Anna is training for a 10K race. The table shows the distance she ran during the first 3 weeks of training. So make a conjecture about the distance Anna will run during each practice for the 4th week. And then figure out how could you test this conjecture. Well, it looks like for Anna, every week she's doubling the distance that she ran. She went a half. If you double that, that's 1 mile. Double that, that's 2 miles. So in week 4, she should be running 4 miles. So how could we test this? We would probably just have to go to Anna's week 4 and actually watch her run for her training. Okay, that's the only really way to test that in real life, but okay. All right, we're going to head back to this circle problem with drawing the chords. So there's a big circle on the next page. They want you to draw all possible chords connecting any 2 of the 6 points. So if we go back to our table really quick, if we have 6 points here, we made a conjecture that the regions doubled every time. So we went from 2, 4, 8, 16. So if you thought about it, how many regions, before we even draw it on the circle, how many regions do you think that 6 points should create? Okay, so now we're actually going to test it. So there's a big circle on this page, page 16, that has 1, 2, 3, 4, 5, 6 points. So what I have you do is you're going to draw all the possible chords there and then count how many non-overlapping regions that you have. Okay, so here is my work drawn in. So if I counted these up, how many regions did we actually have? I did not have 32, right? So what is the number of non-overlapping regions? I only saw that we had 31 non-overlapping regions. So is this the number that we predicted from our table? No. Okay. We predicted that it would follow the same pattern, right? And double. So I predicted that there would be 32 regions, but we were wrong. There only happened to be 31. So how could we further investigate the pattern in the number of regions formed by chords joining n points of a circle, where n represents the number of points placed on the circle? So we knew 6 didn't work. So how could we keep testing to see if that was maybe just a fluke or if this pattern really isn't a pattern at all? Okay. Well, one way we could do that is we could just make a circle and test more points. Okay, so for example, we could make a circle and have, let's say, 7 points on there. 2, 3, 4, 6, 7, and count how many non-overlapping circles there are. So we could do like 7 or more points, right? And then make a conjecture from there. So that's where we have some flaws in these conjectures, okay? So again, it's just an observation that we made. It's not necessarily anything we've proven. It's just from an observation. So they're not always correct, these conjectures. They're just kind of observations. We're making a generalization about it, okay? So let's practice just a couple more, and then we're going to kind of end it here. But let's just look at this, check your understanding. So questions 8, 9, and 10. Zach writes a conjecture that a rule for the first few terms of a sequence. Is this conjecture necessarily true for all terms? Okay, so again, this answer is no. Okay, it's not necessarily for all terms. It might just be a pattern for a certain number of terms, but it doesn't necessarily have to continue for every number in that pattern. Okay. Again, it's just a generalization. It's not a rule. So number 9, the table below represents the function 2x plus 5. Based on the table, Trent conjectures that the value of f of x is always positive. Is this conjecture true? So what he's saying is these numbers down here, they're all positive numbers. So that must be true for any value of x. Is Trent true or not? Well, hopefully, again, you said no. Okay, It's not necessarily true. Now, for the x values that they're showing us, yes, those gave us positive values. And if we continued into this direction, I'm sure we would still continue to get positive values. But if I started going in this direction with x values smaller than -2, well, those values, so say we did -3, for example. If I plug that into my function, 2 plus times -3 is -6, plus 5 would give me a -1. So no, he's not correct, because if I do bigger negative values, I'm going to get negative values out of the function also. Okay? All right, last problem I just want you guys to try. So Monique tosses a coin 3 times. She gets heads each time. Based on this pattern, she makes a conjecture that she will always get heads when she tosses a coin. Is her conjecture reasonable? Why or why not? So go ahead and answer this one for yourselves. Okay. Hopefully, we all know how logic works, right? This is not reasonable. Unless she has a one-sided coin, it's not reasonable. You got a 50-50 shot, right? Every time you flip a coin. So it just happened that she got heads the first couple of times, but that's not always going to happen. Okay? So again, the main takeaway from today is knowing that the inductive reasoning is just kind of recognizing a pattern, and then a conjecture is the generalization you make about that pattern. Again, it's not necessarily a rule. It just happens to be an observation you make. Okay? So I hope you guys had a good lesson and this made sense. If not, make sure you come tomorrow with your questions so we can kind of answer anything that you might have. Okay, and keep studying that vocab.